triple integrals. And so again, I started number 4. But triple integrals, you'll find as we start talking about them, we've actually been working with them all along. Just kind of weird. Right? So I'll take you through the nuts and bolts of it, but you'll see that it's actually pretty straightforward because you've already learned all the stuff that makes the concept of a triple integral tricky, I guess. All right. So the example there, use a triple integral to find a volume between the surface defined by the function below and the region. You know, they give you the rectangular region, which is good. That means by Fubini, it means that the boundaries, the order of integration is interchangeable. So that's good news. What we're actually doing when we find a triple integral, and let me see if I can screw up this diagram. Usually pretty good at messing it up. Which is crazy because I have the whole thing like traced out here for me and I still manage to mess it up every time. All right, so this is X, Y, and Z. So X over here, a little wonky X. Y over here and Z over here. What we want to have is little dx's, dy's, and dz's. I'm going to shrink it down. Right, you know what? I'm just going to hang on to that. And just start stacking them up. All I'm looking to do here is populate my way through the entire region by stacking little blocks upon one another. See, it's already starting to take a walk on me. All right, so that would be one column. See, it looks like a disaster after a while, especially with the labels in there. But that's the general idea, is that we're going to be populating this entire region with all of these little solids, these little rectangular solids, until we've filled up the entire area, the entire volume. And we have the true volume over that interval. Yeah, you see, I've never, like I said, I've never successfully managed to do this. Like a board cube. They're style points, though. It really just looks like it just shaded the whole thing in, but that's what we're doing. And all of that for the purpose of getting the true volume within the figure, right? Just by taking those little teensy tiny infinitesimal little blocks and piecing them all together. Right, so how do we do that? Well, we integrate all of our dz's. And after we do that, right, so that gets all the little line segments going up the ladder. Then we integrate all of those, the collection of line segments that make up the height. We integrate that over x, so we span that out in the x direction. Or y, doesn't matter. I'll do dx. And then once we have that two-dimensional rectangle in the x and z direction, then we take those rectangles and we span those out in the y direction. And so you have all the different permutations of dx, dy, dz that allow for the different ways in which this could be accomplished. The most popular one, or ones, would be the last one that I wrote. Okay, so that's generally the one you want to work with. Typically, we want to work with the z function first, because it's usually the most complicated. And we always want to go from most complicated to least complicated whenever we're dealing with double or triple integrals. So with that in mind, it makes sense that we would take care of the z function first, and then from there, just kind of go with the next complicated function, whether it's x or y. Okay. So in number one, you see here it's asking us again to use a triple integral. Okay, so and this is going to connect with what I was saying before about how we kind of already know this. So here's my z function. I'm going to solve it for z in terms of x and y. Z equals 4 minus 2x plus y. All right, that's not the difficult part. I would be integrating this, a triple integral, with the dz first, then d whatever. I'll say dx, dy. All right, so that's the model that we're going to use. Right, so what we're going to do is integrate, and when we say that we're integrating dz, dy, dx, dy, yeah, that's kind of like a misnomer. We're integrating 1, that constant multiple of 1. So I can kind of assume that. Right, so one single solitary one of those dz's, instantaneous changes in z. All right. So what I'm going to do is I'm going to integrate this from the floor, right? Because it says from the xy plane. Oh, that kind of worked. I went for the highlighter, but xy plane is z equals 0. So that's my floor. I want floor to ceiling. So for the z's, I'm going from 0 to the z function, which is variable, based off the plane 4 minus 2x plus y. And I still have the 1, the dz, dx, dy. I just need those other bounds. Fortunately, I have those other bounds. It's rectangular. -1 to 1 for both the x and the y. So next up is the x's, then the y's. All right, so now what I would do is I'd integrate this 1 with respect to z, which is actually super easy, barely an inconvenience. Antiderivative of 1 with respect to the variable is the variable itself. So z over the interval of 0 to 4 minus 2x plus y, which amounts to just a 4 minus 2x plus y. So then what we're really looking at is the double integral over the interval of -1 to 1 in both cases of 4 minus 2x plus y dx dy. So in reality, what we were doing just now is kind of developing an explanation as to why we were using double integrals to find volumes. The reality is that they're one and the same, at least in certain circumstances, because the double integral gives us the genesis of the z function as being the integrand for the double integral in terms of x and y, right? Because if this were a problem, 2 pages ago, this would be our first step. We wouldn't have done any of this other work. But here we're trying to learn where the triple integral kind of comes into play, right? So when I integrate, it's partial integration, it's 2 variables, so no calculator yet. So 4x minus x squared plus xy over the interval of -1 to 1. So pop in my 1s, I get a 4 minus 1 plus y minus -4 minus 1 minus y. Combine our likes, we're looking at 8. And we have, well, cancellation, it looks like, -1 minus -1. I am kind of not with it today, so let me just go a little old school there. All right, so yeah, we do get the cancellation. 8 plus 2y. And we're integrating that over the interval of -1 to 1 with respect to y. Now, this one's actually easy enough to do by hand. And you find more often than not that's what happens. Like, you have every intention of going to the calculator with that last step, and you're like, oh, but it's just this, I find in most cases, I go to the calculator to avoid having to evaluate the function. I just don't want to do the work. That's part of the thinking there. So 8 plus 1 minus, and we have a -8 plus 1. So it looks like just a 16. Oh, it crashed on me. What on earth? So weird. Oh, at least we saved it. Yeah, so 16 would be our final answer, 16 cubic units. I mean, as far as triple integrals go, it's not really too crazy. The issue is with triple integrals, we can use it to expand beyond just simply finding a volume. We can use it to incorporate additional dimensions. Since we know that finding the double integral can give us volume, then finding a triple integral, if we already know the double integral is giving us volume, integrating that integral would give us an additional dimension, right? So we can incorporate the fourth dimension, right? Now, contrary to popular belief, the fourth dimension is not always time. Time travel movies that have you think that, but it's whatever additional dimension you want to incorporate, right? So maybe temperature. So you have a volume, so a space, a room. You know what the volume is, but maybe you have variable temperature throughout the room. That happens all the time. Might be happening right now, where you're like, oh, there's a draft in here. It's a little cold in this one spot, or it's getting a little hot in this area. Let me open a window. The diffusion of heat throughout the room, that is an additional variable. You have the volume, 3 dimensions, the additional variable being temperature. Right? So that's just one quick example. Now, if you incorporate density to volume, like you see below, if you incorporate density as the fourth variable, the product of density and volume is mass. So the product of those 4 variables would give us a measure of mass. So we could use this to figure out that, for example. All right. So again, another Fubini instance. Compute the triple integral. But this time, we have the 3 bounds given to us. All right. So here it's not the third bound being the function itself. The third bound is the third variable with the function of x, y, z being a fourth variable. So a variable equation. All right. So we would say, and we're using a rectangular base region, so I can do this in whatever order I want. So 0 to 1, I'll do it in the order it's presented. -2 to 2, and then 0 to pi, related to 4y e to the x sine of z. I did z, y, x. All right. So if we're looking at, for example, let's say that this is a density function. Then this would result in mass. Right? Because what we would be doing is accumulating the variable densities over the 3 dimensions. Right? So if this is density, then that whole thing is mass. If it's temperature, then you have an accumulation, a cumulative temperature throughout the room, which is valuable information if you wanted to have a sense of what the average temperature is in a room. Because if you think about it, if you take a thermometer or use a programmable thermostat or whatever, it's only measuring the temperature at its location. If you raise it up higher or raise it down lower or lower it, or swing it over to the left or to the right or obliquely, you're going to potentially get different temperature readings. Probably not drastically so, but you will get different temperature readings. And when that happens, how do you decide what the temperature, the quote unquote temperature is in the room? Do you find the temperature at each and every little incremental change in horizontal, vertical, and I'm out of terms here. Horizontal, vertical, and the XY plane, and then the true vertical, based off of the normal to the surface. These are all things that you could do. You take a variety of different readings and then average it all together, but you could also use a triple integral. So again, I'm not saying that this is density, a density function. I don't even know if this function makes sense for density. Probably not. I'm just saying if it were density, then the result of this computation would be mass. Right? So you get down to the nitty gritty here and you say, okay, well, let's start off with the z's. We're looking at the antiderivative of sine is negative cosine, so -4y e to the x cosine of z over the interval of 0 to pi plug in the pi or the 0, and you're going to get negative or positive 1, depending. So we're looking at first the pi. That's going to give me a 4y e to the x minus, then I plug in the 0, another 4y e to the x, but this time negative. So that's going to total out to 8y e to the x. All right. That's the first part. Next up, the double integral. With a much simpler expression now. Simpler. This was probably daunting 2 weeks ago. It's not so much now, because now that you know you can do it, you can find the integral partially, then it made things a whole lot easier. With respect to y, we're looking at 4y squared e to the x over the interval of -2 to 2. And so pop in either of them, and you're going to get, it looks like a 16. So 2 squared for 16 e to the x minus 16 e to the x. It goes to 0. I don't remember that. Probably screwed up something. What did I botch? Classic Bob. It's weird. No, double check it, I guess. Well, it's 0, I guess. From 0 to 1. So really wouldn't make sense for density. So antiderivative of 0 with respect to x. Well, the antiderivative over an interval of an object with 0 height is going to be 0. All right. So this would have 0 mass because it has a, I suppose, a nonsensical function. But hey, got the job done. Yeah. So I'm going to put a star on the next one. And then I honestly don't remember. I thought I wanted to get rid of this problem, but I can't remember if I'm thinking of the right one. So number 4 on page 84. Oh, you know what? I think I wanted to just modify it. I just can't remember how. I just can't remember how. Well, oh yeah, you know what? Write the triple integral, then evaluate. No, I think I actually changed it. It's weird. I don't know. It's crazy. Anyway, we have this this function here. That's the one that's relevant. This is a quick one, by the way, so I'll get you out of here on this note. All right, so this is the one that we want to integrate over the interval. So it's not going to be too bad. It's just it's the setup. It's always the setup. So if I wanted to integrate this as a triple integral, I'd have my f of x, y, z. Oh, I already have that written, so just 1. And then dv would be dz, dy, dx, you know, whatever you like. All right. So what we're going to do, because they tell us the constraints are x, y, z such that they're bounded by the function or by the sphere x squared plus y squared plus z squared is equal to 9. All right. So it's a sphere, so it kind of lends itself to spherical coordinates, which we'll talk about next time. Right? But what we do have, if we're just focusing on the x variable versus the y variable versus the z variable, you have a maximum distance from center. Right? So x, y, and z are going to have to be within the bounds of that sphere. All right. So all right. So if I want to talk boundaries in terms of z, what I could do is say z squared is equal to 9 minus x squared minus y squared, which in turn would give me the radical plus or minus which I could use as my bounds. Not going to be pretty, but it's doable. Now, if I want to look at this on the xy plane, okay, because what I am looking for is the volume contained between this function and the xy plane. I'd be looking at x squared plus y squared plus 0 squared is equal to 9, which gives me x squared plus y squared equals 9, which makes y bounded to be the square root plus or minus 9 minus x squared. All right. So then it would just be a matter of finding the restrictions for x. You could just kind of look at it here. 9 minus x squared has to be greater than or equal to 0. So you solve, and we're looking at x squared is less than or equal to 9, which means that x is going to be in between -3 and 3. And so you get all those bounds. It's all wonderful stuff. We'd have to put all those bounds in, so I'll just kind of give you the short version of it now. I'd have to put the z bounds here and here. All right, that's that whole z equation, the negative and the positive. All right. So that's this stuff here. So that would be my low bound. That would be my upper bound. Disaster. All right. Then I'd have to do the same thing for the y's. The negative one being the low bound, the positive one being the upper bound. The only place I get any kind of reprieve is with the x's, where it would just be -3 to 3. All right. So that's, I mean, we could do that. That's a nightmare. All right. So instead, what we'll do is kind of work this so that it's accessible using polar coordinates. Right. So the first thing I would look at is my z equation. That could be thought of plus or minus 9 minus parentheses x squared plus y squared. So z would be equal to plus or minus the square root of 9 minus r squared. Then I would look at my x squared plus y squared equals 9. Well, that's r squared equals 9, corresponding to r equals 3. All right. Now, as the the sphere applies, since we're looking for the region that's bounded between the surface and the axis itself, it doesn't seem like we would need the negative part of that, right? But do with it what you will. It's up to you. I'm gonna neglect the negative component of it. I'm gonna say, you know what? I don't need the negative part. We're just gonna go from there. All right. So I'm gonna have a triple integral. It's gonna look very much like what we have here. Get rid of those boxes. They get kind of confusing. One, two, three. We got a one, poor quality one. We bring it in, make a better one. The dy dx gets replaced with an r dr d theta. All right, so my z bounds, it's not complicated. Right? So the z bounds, well, actually, I misspoke, / I was incorrect. We actually will need both the negative and the positive for z, because it's constrained by the function. So negative square root of 9 minus r squared, positive square root of 9 minus r squared. So that's my z. Then I need my r, which is going to go from 0 to 3. And then I need my theta. Well, it's one full trip around a sphere. One full trip around anything is 360 degrees, or 2 pi radian. Right. So right off the bat, we're looking at something that's a whole lot more manageable. Right. When we integrate, with respect to r, right, r becomes, oh, I'm sorry, what did I forgot my dz. Apologies. Can't just get rid of the dz. What are you, crazy? This guy. If only. All right, so it's going to be z going from negative 9 root 9 minus r squared to positive root 9 minus r squared. So that's the difference between the two. So that's 2 root 9 minus r squared. Then we go the rest of the way integrating. So I would take this bad boy, slap an r on it, dr, integrate that from 0 to 3. And then once we get around to it, 0 to 2 pi with respect to theta. So all calculator all the time at this point. So integral 0 to 3, open paren. I'm going to use the x's, so 2x root 9 minus x squared dx. A clean 18. Very surprising. So 0 to 2 pi d theta, 18 theta over 0 to 2 pi, which means that we're looking at 36 pi. All right, so that would be our restricted solution. All right, but it gets at the idea that we're looking at a sphere, and we're essentially looking for the volume within that sphere, and that's something that's verifiable. So we got what we needed, you know, so. Let me get rid of the pi there. So the volume of a sphere with a radius 3 would be 4/3 pi times the radius cubed. So it would be 36 pi, which is what we got using this approach. So we just verified, you know, without using general terms, but we verified the volume of the sphere formula. All right, so I'm going to stop the recording.